Hello everyone. Today we will be solving question number 17 from GATE 2019 question paper. The question is the number of CO stretching bands in IR spectrum of trigonal bipyramidal cis MCO3L2 is what is the so here they are asking what is the number of CO stretching bands in IR spectrum of this trigonal bipyramidal complex. M is metal and L, here they have given that L is a monodentate ligand. So we have to find the number of CO stretching bands in IR spectrum. They have already given the geometry of this complex, cis MCO3L2. It is trigonal bipyramidal. So let's draw the complex first. This M, okay. Cis MCO3L2 means 2L should be in cis position and the other three are CO, CO, and CO. So this is the structure of this trigonal bipyramidal complex. Now, to know that there are total how many II active bands in this molecule, we should know about the local symmetry of this molecule. So the local symmetry around the central atom of metal carbonyls decides the number and intensity of the carbonyl stretching bands in their IR spectra. And the number of IR active bands for a specific isomer can be arrived at by using group theory. So finding the number of carbonyl stretching bands in metal carbonyls is one of the application of group theory. So to start this question, first we have to find out what is the point group of the given molecule. So this is a trigonal bipyramidal complex. For finding the point group, we should know that what are the symmetry elements present in this molecule. Symmetry elements. So one is the identity, symmetry, and the other one is here there is no principal axis CN. Okay, there is just one sigma plane, which is so the sigma plane will be passing through these two, this ligand L and this L and CO. So this is the only plane, that is only one sigma plane is present in this complex. So if a molecule is having only these two symmetry elements, that is E and sigma H, then the point group of this will be CS. So the point group here is CS. Now the reducible representation for cis MCO3L2. We have to find out the reducible representation for this complex. Now let's make three arrows for these three carbonyls. So how we find the reducible representation? This reducible representation is denoted by the character of E and character of sigma H. And how do we find the characters? Characters are number of unshifted arrows for that operation. So if we do identity operation on this complex, none of the three arrows will be shifted. So therefore, character of E operation is 3 and sigma H means if we cut through this plane, then we can see that this CO will remain unshifted. This arrow of CO, this will remain unshifted, whereas 1 and 2, these two will get interchanged. So they are getting shifted. So here the number of unshifted arrows for the operation sigma h is 1. Okay. So this is the reducible representation. Now, next, the reducible representation is broken down into its irreducible components with the aid of character table and reduction formula. So this is the character table for CS point group, and the reduction formula is this, where n species is equal to 1 by g summation over I gi chi reducible into chi table, where n species stands for number of times the species contributes to the total reducible representation. G stands for the order of the group, which is equal to the total number of symmetry operation in the group. So here the total number of symmetry operation is, we can see that there is one E and one sigma H. So the total number of symmetry operation will be 2, and hence the order of the group is 2. Then comes GI. So what is GI? Number of operations in the symmetry operation class I. So here E is also 1 and sigma H is also 1. Therefore GI for both the operations will be 1 only. And then chi reducible, that means the total character of each operation found in the reducible representation, and chi table means the character of each symmetry operation in each species. By that we mean this characters. Okay, so these are chi table, and chi reducible means what we found from this. This is the reducible representation. So chi reducible is this 3 and 1. So now by using this reducible representation, the character table and this reduction formula, we will find out the number of times the species contributes to the total reducible representation. So here are two species, in this case A dash and A double dash. So N A dash is equal to 1 by G. So G is the order of the group, which is 2. Then GI, so this is GI, that is 1 into chi reducible for E, it is 3 into chi table for A dash, it is 1 plus GI, here also this value is 1 into chi reducible means for sigma h it is 1, and then chi table this value is 1 again. So that means 3 plus 1 by 2, which is equal to 4 by 2 and 2. So A dash, this appears twice in the reducible representation. Then coming to the next species, N A double dash, it is equal to 1 by 2 again, since G is the order of the group. Then we will look into this one now. So for A double dash, again GI, that is will be 1 into chi reducible for E, it is 3. Then this value chi table is 1 plus 1 into 1 for chi reducible into minus 1 value of chi table. Okay. So here the value is 3 minus 1 by 2 or 2 by 2, which is equal to 1. So now we can write the reducible representation as twice A dash and 1 time of A double dash. Okay. So from this character table for the species, if it is transforming to Cartesian coordinate, that is Cartesian coordinate x, y or z, then that for that species it is IR active. So here we can see that in both the cases A dash also transforms into x and y, and A double dash also transforms to z. So both of these species are IR active and there are two A dash. So 2 plus 1. That means there are total 3 IR active CO stretching bands. So now since this is a long process to do, there is also one like trick kind of thing which we can by which we can remember easily that there are total how many IR active carbonyl stretching bands for metal carbonyls. So this is the trick. Okay. For highly symmetric metal carbonyls, we get lower number of IR active carbonyl stretching bands. So what are highly symmetric metal carbonyls like octahedral, tetrahedral or DNH point groups? If by octahedral we mean that if there is an octahedral complex with 6 ligands which are same, so this will have only one IR active CO band. Okay, this L is CO here. Also, if there is a tetrahedral metal carbonyl in which there are 4 COs only coordinated, we will get one IR active carbonyl band for that, and same is seen for DNH point groups. Next, for metal carbonyls with lower symmetry, they give higher number of IR active CO stretching bands. So lower symmetry point groups are CS, C2B or CNB. So CS, as we saw in this molecule which was given in the question, the number of IR active bands. So here the molecule which was given was cis MCO3 L2. Okay. So there were the number of IR active CO bands is equal to number of CO in the molecule. So there were 3 CO in the molecule, and also we found out that there are 3 IR bands observed for 3 IR active CO bands observed for this molecule. For C2B also, the number of IR active CO bands is equal to number of carbonyl in the molecule. And for CNV, where N is greater than equal to 3, the number of IR active CO bands is equal to number of carbonyl in the molecule minus 1. So the answer for this question, that is the number of CO stretching bands in IR spectrum of trigonal bipyramidal molecule cis MCO3L2 is 3. To know more about this topic, please refer to the lecture on chemical applications of symmetry and group theory by Professor Manavendra Chandra from Department of Chemistry, IIT Kanpur. The link for the lecture is given here. Thank you.